Hi everyone, welcome to this video on similarity. For some of you, this might be a brand new topic and others of you might have been introduced to it before. We're just going to start from the beginning. So we're going to start with a quick review on congruency. So what does it mean for two figures to be congruent? So figures that are congruent have the same shape and the same size. More specifically, if we talk about two polygons that are congruent, like two congruent hexagons or two congruent triangles, all pairs of corresponding angles are congruent, and all pairs of corresponding sides are also congruent. Okay, so taking that idea and connecting it to similarity. When two figures are similar, they still have the same shape, but not necessarily the same size. More specifically, all pairs of corresponding angles are still congruent, and the ratios of the lengths of their corresponding sides are the same. All that really means is that the side lengths of one figure are multiples of the side lengths of the other figure. So one figure might be 3 times bigger than the other one, or maybe one figure is 1.5 times bigger than the other one. So there's some kind of multiple that you would use to get from one side to the other for all of the sides, not just for one pair, but for all of the pairs. So similar shapes are the same shape, but they could be different sizes. You could think about like blowing something up on the copying machine, like taking one figure and making it bigger or making it smaller, but keeping all of the angles the same. Okay, so here we have an example, our first example of two quadrilaterals that are similar. When you look at this statement here, this symbol in the middle means is similar to. So instead of a congruent symbol like this that we're used to using a lot, this is a similar symbol. So that symbol of one little curvy sign there is called is similar to. So ABCD is similar to EFGH. And just like when we wrote a congruent statement like that, the order of the letters is super important because it talks about what's corresponding. So angle A would be the same as angle E, angle B is the same as F, and so on. And then the same for the sides. So AB would be in a relationship to EF, whatever that ratio is that we're going to talk about today. And then BC would correspond to FG, and so on. So over here on this side, I've written out all of the statements. So here are all the angle measures that are congruent, like I just mentioned, based on matching up the letters. So angle E would be equal to angle E, angle B would be equal to angle F, and so on. But for the proportions, or for the ratios, what we do is we take those pairs of corresponding sides. So we know that AB is corresponding to EF. And if we looked at the ratio of their sides, like what if you put AB over EF as a fraction? You could also do it the reverse way. You could put EF over AB. The key is to be consistent for each of the pairs. So if you make the ratio of AB over to EF, whatever that is, you would get the same ratio if you put BC over FG, the next pair of corresponding sides. And you can do that for all 4 pairs. Let's look at this next example to see that actually in action. So we have two triangles here that are similar. ABC is similar to DEF. We're going to start by making our angle pairs. So we know that angle A would be equal to the measure of angle D because of how they're written in that corresponding, or in this similar statement here. And then angle B, the measure of that is equal to the measure of angle E. And angle C, the measure of that would be equal to the measure of angle F. Then for the ratios. So again, if we just sort of go in order, if we take the side AB and put that over side DE, and we're going to put numbers in here in a second, that would be equal to the next pair, which is BC over EF. And then that ratio should be equal to the third and final ratio of CA over FD. So let's put numbers in here and see how this works out. So AB, we look over at our triangle, AB is 10, and that is going to go over DE, which is 20. And then BC, which is 6, would go over EF, which is 12. And then CA, which is 7, would go over FD, which is 14. So let's look at how these reduce. Well, 10 over 20, that will reduce to 1/2. And 6/12 reduces to 1/2. And 7 to 14 would reduce to 1/2. So we have the same ratio. So the ratio of these two similar triangles would be 1 to 2, or 1/2. So when you do have similar shapes, you're going to see this ratio being the same for every pair of corresponding sides. Sometimes you're going to get a question that will ask you, are these two shapes similar? Are these two triangles similar? Are these two quadrilaterals similar? And this is how you would find out. You would set up the ratio of all of the corresponding sides, and you would look to see if they have the same ratio. And you would have to check every single pair, because you might find that a couple of the pairs are the same, of the same ratio, but that one or two of them are different. So you do need to check them all to see if they are. If you get the same ratio, then they would be similar. Okay, so here we have two similar pentagons. ABCDE is similar to FGHIE. So we're going to fill in these missing blanks. Angle B, you can look here, is probably the easiest, is going to match up with angle G. You can also look at the pictures if that's helpful to you. And then angle E, that one is going to be matching up with E on this side. If you look at the picture of why they're the same letter, because they're sharing this spot right here. And then angle D is matching up with angle I. Okay, so for the ratio pairs, we're looking at AB is set up on top of FG. Those are corresponding. And then on the second part, we're looking at something matching up with GH. So that must be BC. And then AE over FE. So we've got the first and the last. And then ED, so the last two, it should match up with EI. And then we have something matching up with DC. So we have DC here. So that must be IH. And then we have EI. That must match up with DE. Okay, so here we have two examples where we want to decide, are these polygons similar or not? And if they are similar, we're going to give the similarity ratio. So we want to find out, do all of the corresponding sides have a matching ratio from one polygon to the other? So in this first one, we if we just start with this side here, and if you look at the angles there, we've got one marked with 4, one marked with 3. That's going to match up with this side here. Let's make that ratio. So this ratio will be from 1 to 2. So I'm putting the one on the left on top and the one on the right on the bottom. I want to make sure I'm consistent with that same setup for each of my ratios. So if we kind of go around the circle, the next pair will be this pair. So we have 3/6. And then the next pair will be this set, which will be 2/4. And then our final set and we have 5/10. So since all of these reduce to 1/2, that means that these are all proportional. The two shapes are, their corresponding sides are proportional because they all have the same ratio. We also can see that there are 4 congruent angles. So all the angles in one polygon are congruent to all of the angles in the other polygon. So yes, these are similar. And when they ask for the similarity ratio, we typically write it to match the shape. Since we go from left to right, we're going to do our ratio the same way. And so we're going to say that this ratio is 1 to 2. So we typically use the colons to show that ratio. All right, for the second set, let's do the same thing. Let's look for our corresponding sides and see if we can find the ratio of that. So let's start with this side we've got from D to A would match up with P to M, and that ratio would be from 6 to 4 or 6/4. And then the next set would be, if I go around the circle, A, B to M, N, we've got 9 to 6. And then continuing around, and we get from 3 to 2. And then finally, our last pair would be 6 to 5. Okay, let's reduce all of these. So we're going to get 3/2, and we get 3/2, and 3/2, and 6/5. So these are not all proportional. They don't have the same ratio. So no, these are not similar because of that, because they don't have the same ratio. Okay, for example 3, we need to find the missing variables. We have 2 defined, x and y, and then state the similarity ratio. So we know that NMQP is similar to SRUT. We don't have to decide that. We know they're similar. And we're going to find these missing sides. So let's look at what we do know. We're told that MN is 18. I'm just going to underline that here so I can see what that's going to match with on the other side. And that does match with SR, and we know that. So these two are matching, so we can put that together in a proportion to help us figure out the ones that we don't know, since those two are matching and we're given both of those sides. So I'm going to go ahead and put 18 over 30 in a fraction. And then the one that we need to know, which is x, and that's Pn, so that's the beginning and the end, that would correspond to St on the other side. So I'm going to put that in the fraction, and notice I'm going to do it in the same order. So I'm going to do x over 25. I did left to right, made that top to bottom. And we set up a proportion. Once we have our proportion, we are going to solve this. And there's a couple of ways I'm going to talk through here. One, you can always simplify a fraction. If I've got 18/30ths, I can reduce that. Just like any fraction I would always reduce, I can divide by 6. That's going to give me 3/5. Then, depending on what I'm left with, if I can easily get from 5 to 25, like if I can see here, well, I can multiply by 5, right, to get from one to the next. Well, I can do that same thing here, and that's going to tell me that x is 15. And then just to quickly review, if that wasn't an easy thing to multiply, like if it wasn't by a whole number, then we would just use our idea of how to solve a proportion, which is to cross multiply. We would look at the fact that the product of this diagonal would be equal to the product of this diagonal. And I'll do one like that a little bit later so you can see how to solve it that way. But for this one, it was pretty easy. Let's go ahead and find y now. So y is going to be tu. So that's these two. So that's going to correspond with qp. So we're going to start with our same fraction as last time since we knew 18/30ths. So this time I'll just reduce it to 3/5. And then that's going to match up with QP, which is 15 over our y. And then again, this one's pretty easy. I can see that I'm just going to multiply by 5 to get from 3 to 15. So I'm going to multiply by 5 to get from 5 to y. So 5 times 5, and I'm going to get that y is 25. Okay. To find the similarity ratio, what we're looking at is the ratio from every side on the left here, from any one of these sides, the ratio of that to any one of the ones on the right. So that first pair that we did, the 18 to 30, that reduced to 3/5. And just to double check that we did everything right today, if we just check any of the other pairs to make sure we get that same ratio. So for example, we found that x was 15 and the corresponding one to that was 25. So let's see if that comes out to the same ratio. So if we write down 15 over 25, that should also reduce to 3/5, and it does. So the similarity ratio would be 3 to 5. Okay, so I just realized we actually have one more variable to figure out. We have this angle of z over here. And if we look up here, z is angle m. and that corresponds to angle R. And over here, we know that angle R is 115 degrees, so they must match. When you have similar triangles, the angles are congruent, the corresponding angles are congruent. So that means that Z, where can we put this one? Z is 115 degrees. So we have that one. There we have all the variables. Okay, let's move on to number 4. So here we want to find x and y again. And let's look at what we are given. We know that AB is 5. So that would be this pair right there. And that's going to correspond on the other side to DE. And we do know that, and that's 10. So if we put 5 over 10, and then we want to find our x value, which is AC. So that's first and last. That's going to correspond to D to F. Oh, and that's our y. So we can't find that one first because we have 2 missing variables. Let's move on to the next one, which is Z. And Z, which is BC, is going to correspond to EF, and that's 4. So we can do that one next. We've got Z over 4. Well, like before, let's reduce. This is going to reduce to 1/2. And then we can see, well, I can really easily go from 2 to 4 by multiplying by 2. So 1 times 2 will give me Z. So Z equals 2. Okay, so we go back to, we still need to figure out x and y, but since we don't know either one of those, we're going to need to do a different way of figuring this out. Let's look at the angles. They gave us some angle measures in this problem, and let's see if we can figure out how we can do this. So if this is 40, then this must be 40. Because remember, if they're similar, their angles are going to match. And if this is 70, then this one's going to be 70. And let's look at our total. So that adds up to 110 degrees. And then our third angle must be what's left over, which is another 70-degree angle. So now we can see that we have an isosceles triangle. So if these two angles are congruent, then it means the angles across from them, or the sides across from them, are also going to be congruent. So if 10 is across from this 70-degree angle, then that y must be equal also to 10. So y is 10, and then the same thing for x. All right, number 5. In the diagram below, triangle ABC is similar to triangle DEF. And then we're given some different measurements. So AB is 7x, that's already labeled. BC is 4, DE is 7, and EF is x. And we want to find the length of AB. Well, let's see what we can set up here. In the proportion, we know that AB is going to correspond to DE. So let's put that as a fraction. So 7x over 7. That's going to equal BC is going to correspond to EF. So that's 4 over x. So here we do have 2 with variables, but because they're diagonal from each other, that's going to make this work out okay, and they're the same variable. So we can solve an equation like that. So now we're going to do the method I mentioned earlier of cross multiplying, where the idea is that if you have 2 fractions that are equal to each other in a proportion like we have here, we just need to multiply this product. So 7x times x, that will be 7x squared. That's going to equal the other product, which is this way, and that's 28. So 4 times 7 is 28. And then we just solve that equation. So once you show that those 2 cross products are equal, and basically you've taken it out of the fraction form, we have a pretty simple equation to solve, and we're going to get x squared alone. So I'm going to divide by 7. So x squared equals 4. Take the square root of both sides, and we would get x is plus or minus 2. And then we need to see, do both the positive and the negative versions work? In this case, because EF is just x, we can't have a negative length there, so we don't need the negative. So x would just be 2 in this situation. We can't have that negative number. And the question said to find the length of AB. So AB is going to be 7x, which is 14. All right, number 6. We have ABC is similar to DEF. We have our different measurements that are labeled for us, and we want to find again the length of AB. So here AB, that is going to be corresponding to DE. So I can set up x over 4. And then AC, suppose, is going to be corresponding to DF. So like this. So x plus 2 over x plus 6. And again, we're going to cross multiply. So we're going to show that this cross product, which is x times x plus 6, equals this cross product, which is 4 times x plus 2. All right, so if we can distribute, I'm just going to move over here as I show my work. We're going to distribute that through. So it's x squared plus 6x equals 4x plus 8. Because I have a quadratic, I have an x squared in here. Actually, that was a plus sign. Let's get everything onto one side and a 0 on the other side. So I'm going to subtract my 4x and I'm going to subtract the 8. That gives me x squared plus 2x minus 8 equals 0. And we're going to factor it. So my choices for 8 are going to be 1 and 8 or 2 and 4. And I want to get a positive 2 in the middle. So I'm going to use a positive 4 and a negative 2. And when I set those equal to 0, my solutions are x equals negative 4 and x equals positive 2. Let's look back at the diagram and see if both of those are going to make sense. Again, since x is one of the side lengths, we can't have a negative. So the solution for x is 2, but then the answer, or the question wanted us to find AB, and that's just x. So the answer to AB is just 2. Okay, let's go back to congruent triangles for a second. We're going to talk about the different shortcuts that we had learned. Recall that we don't have to always show that all 3 pairs of corresponding sides are congruent and that all 3 pairs of corresponding angles are congruent in order to determine that 2 triangles are congruent. We had congruent shortcuts where we only need 3 corresponding parts. So do you remember the different shortcuts that worked? Let's see. We had side, side, side. We had side, angle, side. We have side, angle, angle, or angle, angle, side. We had angle, side, angle. And then we had HL. So those were all of the congruent shortcuts that work. Let's just take side, angle, side as an example and review what it meant to be, what SAS meant when we used it as a triangle congruent shortcut. This was the long version of it. If 2 sides and the included angle of one triangle are congruent to 2 sides and the included angle of another triangle, then the 2 triangles are congruent. Notice that we have congruent happening here. So if we know that these are congruent to these, then the triangles are congruent. All right, so for example, here are 3 different triangle pairs that are congruent by SAS, by side, angle, side. So triangle ABC is congruent to triangle XYZ, and we can see here is 1 pair of sides, and then we have a second pair of sides, and then we have the angle that is the included angle right between those 2 sides. So this angle here is congruent to this angle here. Because it's the included angle, then the A goes between the 2 S's, so it's side, angle, side. In our second set, we have a pair of congruent sides here. We have by reflexive property, the one that they share, and then they each have this right angle that's congruent in between them. So again, by side, angle, side, those 2 triangle pairs are congruent. In our final one, we have this side is congruent to this side. That's 1 pair of sides. This side, KN is congruent to KL. That's another pair of sides. And then by vertical angles, this angle is congruent to that angle. So again, by side, angle, side. By side, angle, side. It goes in that order, and the angle is in between them. It's the included angle. Those two are congruent. Okay, so in a similar fashion, we don't have to show that all three corresponding pairs of angles are congruent and that the ratios of all three corresponding pairs of sides are equal in order to know that two triangles are similar. We have shortcuts, just like we do for congruency. We have shortcuts for similarity. These shortcuts are very similar to what we had for congruency, and you'll notice a few differences. So here are the shortcuts. We have side, side, side. We have side, angle, side, and we have angle, angle. So there's just three. Let's talk about that last one just for a quick second. Angle, angle. We know that if the angles of one shape or of one triangle are congruent to the angles in another triangle, that those triangles are going to be similar. And we only have to show two angles because of the third angle conjecture. If you know two angles of one triangle are congruent to two angles of another triangle, then that third angle has to be congruent because they have to add up to 180 degrees. So technically, if two angles are congruent, all three are, but we call it the AA shortcut because you only have to know two of them. You don't have to figure out that third one. And then because of that, because two of the shortcuts for congruency, we had angle, side, angle, and angle, angle, side. Because these two have two angles right in these shortcuts, we don't need to find out that third part about the sides. So we can sort of lump those two into this one grouping of just AA. So there's only three similarity shortcuts you have to know. Next, we're going to talk through what do they actually stand for because it's a different meaning of the shortcut. Like what side, side, side means for congruency is different than what side, side, side means for similarity. So we're going to talk through that. Okay, so for side, 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 it says if the three sides of one triangle are proportional to the three sides of another triangle, then the two triangles are similar. Remember that proportional just means that the ratio of those two of the pair of sides is the same for all three pairs. So if the ratio, is from 1 to 3 for one pair, it's from 1 to 3 for the next pair and the third pair. It has to be the same. So if they're proportional, that's what that's saying. Proportional means they have equal ratios. Okay, our next one will be side, angle, side. So this one says if two sides of one triangle are proportional to two sides of another triangle and the included angles are congruent, then the triangles are similar. So it's similar to what we did for triangles for congruency for side, angle, side. It's still talking about the angle that's right between those two sides, like we talked about when we did congruent triangles, even just today. But it's the idea that the angles are congruent, but it's the sides are proportional, not congruent. The ratio of those two sides are the same from one triangle to the next, but the angle between them has to be congruent. Okay, our last one is angle, angle, which is the easiest one to explain. And this one says if two angles of one triangle are congruent to two angles in another triangle, then the two triangles are similar. Now, it might be that those triangles are also congruent. We just don't have enough information if we just are doing angle, angle. So if you wanted to then go further and find that out, we would need to do one of the congruent shortcuts. But if we have angle, angle, that's enough to know that they are indeed similar. Okay, so for these examples, we are going to decide if these triangles are similar or not. We don't know if they are. And we want to check on, based on what we just talked about, are they similar? And then we're going to tell how we know, like what shortcut are we using? So in this first example for number 7, we only have side lengths to deal with. So the only possible shortcut we could use would be side, side, side. We don't have an angle given to us, so we can't use side, angle, side, and we certainly can't do angle, angle. So we want to check and see, are the sides proportional? So if we can see that VT is probably going to line up, since that's the shortest one, with QS. Let's put that together in a ratio. So I'm going to go from top to bottom, so 42 over 15. And then let's just take the longest one, which would be 84, and that's going to go with 30. So we want to see, is this true? Are these equal? Do these ratios, if we reduce them, are they the same? So I can see, let's see, if I just reduce this right side by 2, if I divide this by 2, I'm going to get 42. If I divide this side by 2, I'm going to get 15. So right away I can see, yes, they are the same ratio for those two pairs, but we also want to check that third set. So let's take 70 over 25. And I can't reduce it to 42 over 15, but let's see if we can reduce all three of these to the same thing. So let's go back to the first one, 42 over 15. I can reduce that one, let's see, by 3. So 3 goes into 15 5 times, and 3 goes into 42 14 times. And I can, of course, do that same thing here. And from 70 to 25, I can reduce both of those by 5. So 5 goes into 25 5 times, and 5 goes into 70 14 times. So we have the same ratio for all three of them. So first, yes, they are similar. So we're going to fill in this shortcut in the right order. So TUV. So T starts at what looks to be the right angle. And on the bottom, that would be Q. And so that would go from T to U, so Q to R. So QRS would be our similarity statement. TUV is similar to triangle QRS. And then we want to give, how do we know that? When we use side, side, side to figure that out. And finally, oh, it didn't ask us to give the ratio, but let's just give it anyway. The similarity ratio would be 14 to 5 from one triangle to the next. All right, number 8. So in this diagram, we are given all we have is some angle measures here. And based on what we see, the angle BCE, that's different from the other two. You can see we have a single mark there, and then we have a double mark up here, and then a triple over here. So those are all different angles. We also know by vertical angles that this pair would be the same. So we have one pair of congruent angles, but we don't have any more. We don't even have AA here. So this is not similar. So no. These are not similar. Okay, for number 9, we are given one pair of angles. We have 61 and 61 for that pair. And then we do have a pair of vertical angles here. And so we do have AA. So by angle, angle, we can declare that triangle HGF is similar to triangle HTS. We made sure we went from H to G to that 61, so we go from H to T, the other 61. So that's in the right order. All right, number 10. Let's see, I have one pair of corresponding angles. So we have an A, and then we have these two sides. So we're looking at possibly doing SAS, but we need to see if the two pairs of sides are proportional. Are they in the same ratio? So if we start with this UW, which is 9, that would correspond to 21 on the other one. And then from U to V, that's 18. And that would correspond to F to G, which is 42. So we want to see if these come out to be the same once we reduce them. I can reduce 9 and 21 by 3. So if I divide by 3, I get 3/7. And if I divide 18 and 42 by 6, 6 goes into here 3 times, 6 goes in there 7 times. So yes, these are proportional, which makes the triangle similar. The shortcut used here is side angle side. And to finish my similarity statement, I would say triangle FGH is similar to triangle U, since that has to match up the 76-degree angle. And then it went F to G, so down the longer side here of the two. So we want to go U to V, and then W. All right, we have two left here. Number 11, we are given some side lengths here, and we can see that, let's see here, we've got this part is 56, and then this whole part is 88, which we can figure out what that leaves for this. So 88 minus 56, that would be 32. We can do the same thing on the other side. If this whole thing is 143 and this is 91, then we're going to need to find this part. So 143 minus 91, that's 52. Okay, let's check on some ratios here. So I'm going to stick with that green pair. If I'm looking at this triangle right here, this side is 52, and then that would correspond to this bigger side of this bigger triangle, which would be 143. And then to move to the red side, 32 would be the side length of that smaller one. And then 88 would be the side length of that larger one. So we want to see, oh, and let's do the third pair while we're at it. Let's see if this third pair, which would be the bottoms of 44 and 121, we want to see if all of these are indeed the same. We don't know if they're equal yet. All right, let's see what we can reduce by. I'm going to start in the middle here. 32, I can divide by 8. 88, I can divide by 8. And 44, I can divide by 11. And 121, I can divide by 11. And 52 and 143, I'm not too sure, but I know that 4 times 13 is 52. So let's see if we can divide by 13. 13 goes into 52 4 times. I bet 13 goes into 143. Let's check that out. And it does. 143 divided by 13 is 11. Okay, so they are similar because we have 3 proportional ratios, and this means that we're using side, side, side as our shortcut. And to put it in order, so we're going F, E, D here. So F, E, D. That's the bigger triangle on the outside, which means that we would do F, R, S to match up with that. Okay, number 12, last one. So here we have one pair of congruent angles. We know that that one is congruent to this one here. So let's check on our sides and see if they are proportional. So if we look at the smaller of these two, that would be 9, and that would need to correspond on this side to 27. And then the last one would be 10 over 30. And let's see if those are equal. If we divide each of these by 9, I'm going to get 1/3. If I divide each of these by 10, I'm going to get 1/3. They are proportional, so therefore by side, angle, side, triangle TUV is going to be congruent or similar to triangle CDE. I started with that congruent angle, so T was congruent to C, and then this went to the longer of the two sides towards that. So we're going to do the longer of the two. That's why it's CD and then E. All right.